So I'm going to be telling you about how we can use chemistry for the second quantum revolution. And the goal here is to use chemistry as a bottom-up approach to synthesize molecular qubits. And I'm going to give you a giant propaganda introduction for why chemistry is great, because I assume some percent of you are physicists and should be reminded pretty much every day that chemistry is great. So let me tell you a little bit about this and why chemistry is a powerful approach. The other thing I will figure out how to do is to advance to the next slide, which, woohoo, okay. So a chemical approach to quantum information science is, I think, really appealing. And I'm not the only one who thinks that this is really appealing. One of the first quantum computers that was ever created is this molecule shown here. And so here you see what is actually properly an organometallic molecule. Can you guys see the cursor when I'm waving it around things? Okay, I'm going to pretend you can. So you have iron with a carbon bond. And what you're seeing here is a molecule where the nuclear spins are qubits, right? Things that can be put into a combination of up and down. And so here we have the fluorines and the carbons are the individual qubits. And this, as you may know, is an incredibly elegant example of an implementation of Shor's algorithm to factor the number 15. Now, when I give this talk to chemistry audiences, I make fun of physicists, and I say that because the physicists were trying to communicate to a general audience that even included chemists, they put the prime factors of 15 in the abstract. So those prime factors are 3 and 5, and this molecule was used to, in a 300 pulse NMR sequence, factor 15 into 3 and 5. Now, there are a lot of reasons why this is a genuinely compelling and awesome example of the power of quantum computing, but what I'll draw your attention to is why a molecular approach is important, and I think this molecule shows it very nicely. A molecular approach is important because in this molecule, you have precise control over the distance between every one of your qubits. This level of sub-angstrom control is unique to molecular chemistry. You don't get this level of spatial precision in superconducting qubits. You don't get this level of spatial precision in pretty much anything. Not only can you control every aspect about your individual qubits, but you can control all of their separations. And that's something really powerful. Now, you may be aware that nuclear spin or molecular qubits containing nuclear spin aren't a popular area. And actually the reason for this is very chemistry based. So if you're thinking about a frequency addressable approach to this molecule, let's say you have your different 7 resonances shown here, right? Now, if you were to like magically tack on another fluorine, you would move all of the other resonances, and everyone who works with molecules knows that, but that's actually a problem. And when you think about scaling this, you really can't get past 7 atoms for the reason that any organic chemist who takes NMRs all the time knows every additional atom that you put in moves around all of your other resonances. And so this is a problem. Now, one reason that this is a problem is because nuclear spin is relatively small in magnitude. If we want to take a different approach, what we're focusing on in my lab and in probably pretty much all the other talks in this symposium is electronic spin. So electronic spin has a lot of advantages. One of them is the much larger magnetic moment, and the other is the much faster gate time. And so nuclear spin, it takes a long time to flip it. Electronic spin is much faster. And so those two things suggest that electronic spin-based qubits are a very compelling approach. Okay, so how are we doing this? And I'm going to just continue to advertise a bottom-up molecular approach to making these atomically precise systems. Okay, so if we want to do this, we can not only create systems that are that have very precise control over distances, but we can tune everything and understand all of the variables by making simple substitutions. So we can control the identity of the metal atom. We can control every part of the ligand, the organic moiety bound to the metal. We can modulate the ligand field and change the d orbital splitting accordingly, or the crystal field splitting states in a lanthanide accordingly, for example. We can also change the spin delocalization. And in addition to that, we can modulate the extrinsic factors. And now for the rest of this talk, I'm going to compare molecular-based qubits to what you could argue are some of the best spin-based qubit candidates out there. And the best spin-based qubit candidates out there, you can argue, are defect-based materials, where, for example, you take a chunk of diamond and you bombard it with ions, and you create this like beautiful scatter shot of defects where you have these, well, you have many defects, but one of interest is this anionic nitrogen vacancy pair defect, the NV center. And those spin-based qubits have a lot of advantages, and I'll talk about that throughout my talk. But when we're thinking about the advantages here, one thing that you can't do is you can't like magically make diamond disappear and replace it with another substrate. Nice thing about these molecular systems is you can actually modulate the extrinsic variables as well. So you can change the solvent, you can change the counterion, you can put them in different matrices, and you can even connect the different nodes of molecules, mimicking the NMR-based approach to control the distances between your candidate qubits. So you can kind of think of this as a vision for chemistry, where we can move from understanding, much like in condensed matter physics, the properties that are inherent to a single unit, the additional complications that occur when you have 2 units as opposed to 1, and then finally the additional level of complications and emergent properties that occur when you move into an array. And having this level of reproducible control enables us to answer questions at all of these length scales, which I think is really exciting. I told you I would do a lot of advertising for why qubits are important. Why molecular qubits are important. Okay, this is really difficult, not being able to communicate with an audience. I admire everyone who's successfully done this so far. Okay, so there are 4 different areas that I'm going to talk about, and everything I deleted is in the 4th area. The areas that I'm going to talk about today are how we can use these systems to gain fundamental insight into the variables that contribute to decoherence. I'll talk about maximizing qubit performance within these molecules by, again, precise control over the environment. I will, similar to what Jonathan just spoke about, I will talk about atomically precise arrays and clock transitions in them and how we can think about different types of scalability. And then finally, I will talk about briefly about our complete failures to make optically addressable qubits. And because I think it's good to end a talk on a note of failure. So, okay. So what are we doing? So one of the first questions that we wanted to answer, and honestly, one of my favorite things that we've gotten to work on, is asking a really simple question of how the distance between an electronic spin and a nuclear spin impacts electronic spin coherence. So if you want to do that, then you want really fine-tuned control over a system. So let's say you have an electronic spin and you want to controllably space a nuclear spin some number of atoms away from it. In between those spins, you need nuclear spin-free atoms. And so this creates just a super fun synthetic challenge. Most of the work we've done has been with binary carbon sulfide systems. So what you can imagine is taking a metal, let's say vanadium, because that's what will appear on the next slide, and creating a ligand comprised of just carbon and sulfur and punctuating that with some protons. And that's exactly, again, what you're going to see on the next slide. So my first student, Michael, these students that join your lab in your first year, they're special people in the best possible way, synthesized this series of molecules. And so the green, I don't know if you guys can see my laser pointer mouse, so I'm just going to say the green atom is vanadium, and you can see these protons that are spaced out by these binary carbon sulfide ligands. And contrary to usual color conventions, I've colored the protons in different colors. Okay, and so we can control the distance. And this is, and one reason I mentioned in the previous slide that I colored the protons is when I actually give this talk to an audience of people, I make them guess which one the pink one is. But since I don't have a proper audience, I can't force you guys to guess, which is a lot less fun. But okay, what we see is that one of these molecules, and these are data at 40 Kelvin, we're eliminating we're not eliminating. I'm not looking right here at the higher temperature data because that's really phonon dominated. And if we want to get into the impact of the nuclear spin, we need to look at the lower temperature data where the nuclear spin effects dominate. So the pink dot and I'll just show the corresponding molecules, has the protons most proximal to the metal center, which is in a way immediately counterintuitive, right? Because if you think about two magnetic moments causing decoherence with each other, then you don't think about the two things that are closest together. But if you actually think about the process, it starts to make a little bit more sense. So I don't know if you guys can see me, so my usual literally flip-flopping my hands might not be effective. So like, let's say you imagine taking your hotel room key for your hotel room in Denver and your credit card and flip-flopping them against each other. That's going to erase the information, right? And this is the same thing that erases the information between two magnets. Now, let's say that your hotel room key card was actually a much stronger magnet, and you have two neodymium bar magnets that are bound to each other. It's actually really hard to make them flip-flop, and it's something that you need to use a relatively large amount of strength to do. And this is the same idea. When your two magnetic moments are really close together, they don't flip-flop enough, and you end up getting less contribution to decoherence. And as you continue, you have a larger contribution to decoherence because they can flip-flop. And I have an animation on the next slide. Now, this is a theoretically defined concept, and we were able to measure it using our molecules, which I think is really exciting. So this is called the spin diffusion barrier. And this is something which is important not only for quantum information, but also for orthogonal and very exciting areas like dynamic nuclear polarization, NMR spectroscopy. I have that written out on a later slide, and I try not to say it without it being written there. But DNP is a really important area that I'll talk about in a couple of slides. So how does this work? We have our flip-flopping spins that contribute to decoherence, but then we have our tightly bound spins that don't sufficiently contribute to decoherence. And then we have our diffusion barrier. Okay, so this is just like a way to use synthetic chemistry to measure a fundamental physical property that otherwise really cannot be measured. And so I mentioned that this has impact in DNP, and it has a lot of impact in DNP, and we're currently collaborating with Sungi Han at UCSB. And if the people who are listening don't know her, Sungi is awesome, and you should invite her to give all the talks and seminars because she's really creative and cool. Anyway, so Sungi studies, among other things, DNP NMR. And if you think about this, what you're doing with DNP NMR is you're harnessing the much larger magnetic moment of an electronic spin relative to a nuclear spin to transfer polarization. So NMR is famously a very insensitive technique. You're using radio waves, right? The energy separation between your upspin and your downspin, nominally, right, is a very, very small quantity of energy, which means that at the temperatures that an NMR experiment is executed at, you have a very small population difference. And so that leads to the famous insensitivity of NMR, like 1 spin in a million is polarized, depending on your field, temperature, etc. So if you can take the much larger polarization, the 3 orders of magnitude larger polarization of an electronic spin and transfer it to a nuclear spin, you can get much better resolution. This is important for a lot of applications. What I've shown here is probably the most common application of DNP NMR, which is biological systems, where you want to be able to see small amounts of things. Other areas where this is important are nuclei that have low spin abundances, like oxygen. That's very important. And in DNP, it's known that you're transferring the polarization of the electron to the nuclei, but it's not known which one. So let's say you're doing this in solution. And okay, there are 2 types of diffusion I'm going to talk about: the spin diffusion barrier, and it spins literally diffusing around. You guys can't see my hands. This is not helpful. Like water. And so you transfer the polarization from the electronic spin to a nuclear spin, but then that spin moves, right? Because it's water, let's say, and the nuclear spins aren't in the same place for a measurable quantity of time. And so by the time you observe the polarized spin, you don't know which spin it was transferred to. One reason this is really important is if you want to think about questions like endogenous DNP. So polarizing something, for example, within a protein and mapping out the local environment. Now, these are like really cool problems. You could understand catalysis better. There's a ton of reason this is important, but first you have to understand which spins are being polarized. So as we're calling them, molecular rulers, and full transparency, this is on the archive, the new Chem archive actually, not like the proper archive. But this has been rejected from like 5 journals so far. That means it's good, right? Okay, so anyway, what we're doing is we're using our molecular rulers to measure this barrier and to see effectively which spins are polarized to lay the groundwork for future endogenous DNP. And this is also, incidentally, the first time vanadium, or a transition metal other than chromium and manganese, has been used for DNP. 99.99% of the work in this field is on organic radicals. And so being able to expand the toolkit of metals you can use for DNP is really powerful for these approaches. So, okay, we see the same thing. We see that the spin diffusion barrier acts to prevent the first sphere of protons from being polarized, and we first see polarization at the second sphere, which I think is pretty cool. Okay, so that's all I'm going to say about fundamental knowledge. I'll move into discussing maximizing qubit performance now. And I will continue with this fun, honest presentation. Okay, so one of the first things that we decided to work on was to see how good we could make a molecular qubit. So these anionic NV centers in diamond, for example, this is an apples to apples comparison, have coherence times of about 600 microseconds. And that number is chosen for a non-isotopically enriched sample with a similar defect density to things that we can measure, etc. Okay, so 600 microseconds. Now, before we started working on this, I think that the longest molecular coherence time was on the order of 10 microseconds, and the vast majority of papers published in this area were in the nanosecond regime. And I think, and that doesn't, and I'm sure many people possibly hidden on this call have contributed to much longer coherence times both since then, right? But I think that from the non-molecular community, from the solid state community, there's a bit of a perspective of, you know, molecules are useless because we're comparing nanoseconds to almost a millisecond coherence time. So why keep pushing? And so what we wanted to do was to see, is this true? Could we make the best molecule that we could make and see what its coherence time was and see if molecules are realistically in the game? And so here I was so lucky to, oh, I want to know if Joe is on this phone call. Okay, anyway. So here I was so lucky to have this amazing postdoc, Joe Zadrozny, who may or may not be listening. Hi, Joe, who took this molecule, which is vanadium, encased in this binary carbon sulfide ligand field, which, as we remember, is pretty much nuclear spin-free. And Joe took some measurements. So we can see that at 80 Kelvin, we can still measure T2, which is pretty exciting because getting up to 77 Kelvin is pretty important for some biological applications. He could also subject this to a nutation sequence, which effectively demonstrates that we can measure the qubit in different orientations, and that we observe these so-called Rabi oscillations, which is pretty cool and shows that we can actually put the spin into multiple orientations. Joe then made a series of these nuclear spin-free molecules and observed the same thing. And so once we had this molecule, we went from the intrinsic properties to the extrinsic properties. And Joe put this molecule in a series of different solvents. And what you can see is that by going from proteated nuclear magnetic moment 2.79 to deuterated nuclear magnetic moment 0.86, I'm probably telling you guys all things that you have memorized so well, we double the coherence time. And that's exciting. But we went from 3 to 6.5 or so. We want to compete with 600. So this, this is kind of terrible, right? But I was lucky to have Joe. And so we thought about this a little bit more, and we thought, okay, well, what is diamond fundamentally? And so diamond is obviously really precious and really expensive because it's a chunk of a nuclear spin-free substrate. So we decided to take the closest thing we could get to putting our molecules into diamond. And that was putting our molecules into CS2. And so carbon disulfide is a convenient nuclear spin-free solvent, which you can think of as fake diamond, except it's much smellier. And so Joe was able to dissolve this molecule in CS2 and acquired some measurements. So we got pretty excited because we changed the unit on the x-axis here. And Joe was able to subject this again to this mutation sequence. And what you can see here in the inset is the time to flip a spin, which corresponds to a gate that you can do with a single spin. And that's a NOT gate. I also sometimes make people guess that, but for the most part, they refuse to. Anyway, that's a NOT gate, turning it over, and so the gate time is 17 nanoseconds. And so if you compare this to the coherence time, then you get a sense of how many operations you could do. So what's the coherence time? Okay, so if we look at this, our molecule in CS2 is in purple. The molecules I showed, the solvent dependence that I showed you before is there. The prior record is also indicated here. And if you remove the log scale, then it looks like we really accomplished something. But more seriously, if you bring this back to comparison with some of the solid state candidates like the anionic NV center, you can see that we're comparable. And I want to be clear, this doesn't mean this molecule is replacing an NV center. What it does mean, not for our molecule, for the whole field, is that molecules really can be competitive with these other spin-based candidates. And I think that this is a really important proof of concept that helps support all of our work as a field. Molecular chemists and quantum information, I mean. Okay, so Jonathan, if you're there, how much time do I have left? I haven't been listening to myself talk well enough. Okay.
How much time does she have left? You have 8 minutes including questions, is that right? No, 8 minutes not including questions.
Oh, okay, cool. Yep. So perfect. Okay, so one thing that I've talked about is how wonderful that original nuclear magnetic resonance molecule was that used the nuclear spins to factor the number 15. And the key thing that exploited is the controllable distance between two qubits. And this is important across all applications of quantum information science, from quantum computing to quantum sensing, where knowing the distance between your sensor and an analyte is pretty important, especially if your analyte is a magnetic moment that decays as 1 over r to the third. So being able to control the relative distance between your qubits is really important. Framework chemistry offers a way to do this. But the problem with frameworks is that they're actually relatively magnetically noisy environments. And I'll skip most of this intro because Jonathan really gave a great intro. But I'll say that we tried to measure a bunch of frameworks that had individual qubits in them, potentially. And we really failed to. And we thought, okay, how can we make something less noisy? And so we thought, okay, we're used to thinking about Zeeman transitions, but if we want to insulate against magnetic noise, then what we can do is we can exploit a clock-like transition where at an avoided level crossing, you have this region of zero slope, which is insensitive to magnetic fluctuations. And they're really elegant proofs of concept. Jonathan highlighted them. We have references here that inspired us to do this. And so then we thought, okay, how specifically do we do this as chemists? And so to do this as chemists, what we thought is we want to create a system where we're mixing two elements. And the elements that we want to mix are spin, I think I have this, excellent, are nuclear spin and electronic spin. So we're looking for something that has a very large nuclear spin. So we have multiple transitions. Multiple transitions create an internal control, a Zeeman-like transition, along with a clock-like transition. And we also want a really, really strong mixing parameter, a hyperfine coupling parameter A. And we want that so we spread these transitions out a lot, both to make the Zeeman transition as Zeeman-like as possible, and also to make it more likely that a commercial spectrometer will be able to read these signals. Okay, so how do we do this? Well, one of the first elements that we thought of was cobalt. So cobalt's almost purely I = 7/2, which is fantastic. but cobalt 2 plus suffers from being almost entirely high spin. So we thought, okay, how do we drive cobalt 2 low spin? And if I was giving this talk to a biology audience, I would tell them that we did this the same way biologists solve their problems, which is by putting it in a porphyrin. They don't think that's funny. Okay, so we took the cobalt and put it in a porphyrin. And if you see that, you see that this is actually the reason we wanted to go for cobalt in the first place. The unpaired spin now resides in the dz squared orbital, which hybridizes by symmetry with the 4s orbital, thereby leading to nuclear spin density at the nucleus, which causes a huge hyperfine coupling parameter, which is exactly what we wanted in the first place. Okay, and so like it does this useless diagram that has no quantifiable information. Does that actually work? And the answer is yes. Which is not on the next slide, it's on the one after that. Okay, so the answer is yes. But then what we had to do is we had to find a framework that incorporates this motif. And we were fortunate that Joe Zhao at Texas A&M had synthesized this framework inexplicably named PCN224. And so this framework incorporates this motif, and we were also fortunate that my colleague Dave Harris had acquired X-band EPR data of it. These X-band data clearly demonstrate that the hyperfine coupling parameter is as large as we hoped. But this is not the strong mixing regime. We had to move to lower frequency. And so Joe, again, Joe's awesome, was able to find a 3.6 gigahertz EPR at UIUC in their user facility. And there we expected that we would see both a clock-like transition and a Zeeman transition. And you can see from his data, that's exactly what we saw. The clock-like transition lives for an order of magnitude longer than the internal control, demonstrating this is a viable way to create networks of qubits. Okay, and so I'll just briefly say that we also extended this work to systems which are not clock-like, because we observed that we could measure the non-clock-like transition. And we thought, okay, well, this is cool too, because this enables us to have a system where we know where every spin is, like in the nuclear spin system, where we can see the contribution of every sphere of spins to decoherence. And so we use these data to model, for example, the sphere of spins 13.5 angstroms apart, et cetera, and see which ones contributed to decoherence. What Raymond found is that the spins that were 50 angstroms away no longer contributed to decoherence, so 5 nanometers. And so we're working on following that up now. Okay, in my last couple of minutes, I'm just going to say very briefly that one reason that the anionic nitrogen vacancy pair defects in diamond that I've been saying we're comparable to are very exciting is not just because they have long coherence times, it's also because you can read information in and out optically. Now that's very powerful. So why does that work? Very simply speaking, it works because you have a very specific electronic structure that enables it. And this electronic structure, this specifically is a diagram that we made. There are a million of these diagrams that are all more accurate than the one that we made. But this effectively works by having an optical pumping scheme that enables you to polarize an energy difference, which is 0.1 wave numbers, using optical radiation, which is insane, but awesome. Okay, so is it possible to replicate an electronic structure of diamond in a molecule? So maybe, right? Like when we think about these systems, we think we put a ligand field on a metal. That ligand field strength gives you the optical excitations. By changing your ligand field strength, you change where you are on the diagram. You can modulate this by changing your donor strength, and you can also modulate coordination number to impact this. This is what we think about all the time. We wrote a ChemCom article about our failures to do this. It's one of the things that I've had the most fun working on. So this is literally an article about failure. It's really fun. Anyway, you can think about different geometries that would enable such an S=1 system. You can think about choosing metals that would be appropriate for this, and then the symmetries that would follow, and then where you would want to be on your Tanabe-Sugano diagram. And I think all of that is a really fun thing to think about as an inorganic chemist, and I removed all my other slides. So the last thing that I want to say with regard to this is that I think that a molecular approach to quantum information is most powerful in a 5 to 10 year time frame for the area of quantum sensing, where you're exploiting inherent quantum properties in a system to sense something in a more precise way. And I think that if we want sensors that are analyte specific, which is kind of the definition of a sensor, then molecules that are tunable are a very powerful class of candidates. And I think that there's just a ton of potential here. And I want to just like evangelize even more and say everyone should work in this field. Okay, I have a group. They are awesome and do everything. And some people fund me to do some research, and I have collaborators, and they are awesome. This is just a small list of our collaborators. That should be much longer. And thank you for your attention, such as it is in this meeting. And I am happy to take questions for the next couple of minutes.
Great. Thank you, Danna. That was a wonderful talk. So there is time for questions. So here's a question from Charles Collett. Carbon sulfate, it seems to work great for vanadium. Do you know how well it works for other molecules?
Yeah, so sorry. Okay, so these binary carbon sulfide ligands work differently on different systems. We published a chromium system, and we've worked on some other metals as well. I think that they're hard to work with, right? So I think that there is a lot of modularity in terms of the metals that they'll work with. You want to be careful with systems like copper, which have the potential to go metallic. These ligands were invented in the, what do you call it? The molecular metal field, the molecular superconducting metal field, and as charge transfer salts. And so just making sure that you stick with things that you can identify as being paramagnetic rather than stacking into metallic configurations with electron delocalization is the hardest part of working with different metals.
Okay, thank you. So I have a question. Of course, I'm most interested in the clock transitions. So if you have these clock transition systems in this metal organic framework, can you get them to talk to each other? Can you get any sort of like controlled knot or other qubit type operations going on?
It's a good question. That's not the first system that we would go after that in. I think that a molecule would be a better choice because you can specifically identify two sites and know where they are.
Yeah, that makes sense.
That's all I got for now.
Okay. So here's one from Jia Chen. For the optically addressable qubit, do you need smaller crystal field splitting? If so, is 4, 5, D, or F electron the way to go?
Okay, so I think it depends on the optical setup that you want to integrate with. And so there are a lot of questions that deal with the specific optical decisions that you're going to make. So I would say that it depends what your laser is. And then you want the thing that has the right frequency for the right laser that you have.
Mm-hmm.